It was very helpful to have the poll at the beginning of this because there were a lot of words that I'm going to cherry pick for the next 30 minutes and try to work them into the next presentation. But essentially, what I want to talk about is using WebAssembly as sort of the unit of execution and deployment for serverless and why that would be a good idea and what are some of the reasons why one would think that would be a good idea. So a little bit about myself. I'm the CTO and co-founder of the Fermyon company, created a spin project there. In the past, I worked on a bunch of open source projects. I spent about 7 years at Microsoft working in a research and development team, working on cloud native Kubernetes ecosystem at a sort of intersection of distributed system security and developer experience. So WebAssembly fits right in the middle of that Venn diagram. When I'm not at a computer building mechanical keyboards, I'm most likely on a bicycle or listening to classical music. So if you want to follow along or get in touch, you can find places to do that in the bottom. A little bit about Fermyon. Started a company back in November of 2021, and we had a very, very simple goal, and that was we identified WebAssembly as having a technology with a huge potential, and we wanted to build really, really cool stuff with it. And so that's why we founded Fermyon in November of 2021. Since then, we've released the Spin open source project, released Fermyon Cloud as a sort of managed way of running serverless WebAssembly, released a couple of Kubernetes-related projects with SpinCube and our platform. And a lot of Fermyon employees are core contributors and maintainers to ecosystem projects. The most important one that I want to highlight here being WoSC10, which is the WebAssembly runtime that underpins everything that I'm about to show you and how we run and execute WebAssembly. So before getting too deep into talking about serverless, I want to be very clear in how I'm going to use the word serverless. I'm not claiming this is the definition by any means, but when I'm going to say serverless, I'm most likely going to refer to function as a service, and specifically the programming paradigm and the programming model where a developer does not write a server process, but they write a handler function. And so if whenever I'm going to say serverless, you can substitute it for function as a service or for a function in the same way that AWS Lambda popularized function as a service. And again, very, very aligned with the use of the word functions. I mentioned in the beginning that I spent about 7, 8 years at Microsoft. Before being in a team working on Kubernetes related projects, I worked on Azure Functions and built a Go worker for Azure Functions. So that was around 2016, 2017. So I've been talking to developers building serverless functions and have been on the building side of serverless platforms for quite a while now. And from both of those perspectives, I hear a lot of converging reasons why developers really, really love writing functions. And just two buckets of reasons. The first one, they just really enjoy writing application logic and not thinking about writing a socket, writing a daemon, writing a server, deploying it, packaging it up as Kubernetes, right? There are places for all of those, but if your job is to write application logic and to write some business logic and add value, you really want to minimize the time spent outside of that. And the function as a service paradigm really lets developers focus on that. Of course, there's a big asterisk to scenarios that fit well to the serverless paradigm, and that's not all of them. And then the other reason why developers enjoy working with functions and serverless is they don't have to think about scaling up or down or being charged for idle resources. And there's a big caveat here around platforms that still use and expose VMs and dedicated plans, where you're still actually charged for idle resources, but that's a conversation that we're going to get into in a bit. But there's always a but coming after. I really like building serverless functions. I've always experienced the but, the second part of that statement, which is, but why do I have to rebuild my serverless function if I need to run it on ARM64? And on top of that, I thought it was JavaScript, which didn't really care about the underlying CPU architecture. So why do I have to rebuild my container to push it to ARM64? Very, very high on the list is also, why do I have to wait for some time upwards of 200 plus milliseconds for my function to start? There are scenarios where waiting 4 to 100 milliseconds for a function is totally reasonable. And then there are scenarios where functions are on the critical path, whether that's a checkout cart, whether that's some other critical function where 200 milliseconds or sometimes more is just unacceptable. And there are uh, enough serverless platforms out there where 200 milliseconds for a cold start is the norm. And then vendor lock-in was one of the words that was on the poll earlier today, and I keep hearing vendor lock-in as a big question for serverless a lot. Once I build my function, can I run it anywhere else, or am I locked in into this platform and I'll have to rewrite it if I want to run it anywhere else? And then ease of use is another one that I'm going to cherry pick from the poll. And the way I keep hearing it is developer experience for this particular platform or this particular tool can be a pain. And I will come back to developer experience in a bit as well. And um, this is somewhat of an oversimplification, but a lot of the underpinnings and a lot of the reasons for those stem from the function being executed still inside a micro VM or a container. And if you think about portability and binary size and by extension cold starts, we are experiencing these because of the unit of execution being micro VMs or containers. And I want to note that there are incredibly successful platforms such as AWS Lambda and a lot of others that have achieved incredible commercial and technological success using Firecracker, for example, as the basis for their FAS offering. And the optimizations they managed to build into this platform is amazing. And so is the research around optimizing micro VMs and containers. And so this is not a knock on micro VMs or containers or any of the research around it. But questioning on one hand, why are we experiencing things like cold starts or portability issues, and whether there's an alternative, and what are the drawbacks to these alternatives. And at the end of the day, as someone building a platform for running serverless workloads, I have a choice. I can either over provision and pass costs to end users and waste energy, or I can under provision and pass cold starts to end users. And all of the research that we've seen so far, and that is ongoing on micro VMs and optimizing functions and cold starts, really work on minimizing the time where our function or our infrastructure is either under provisioned or over provisioned. And at the end of the day, our job is to try and minimize and try to match as closely as possible the curve for the demand. And so by extension, can we pass both cost savings and fast startup to users? And really, again, an oversimplification of the problem, but I think this graph matches very closely the job that we as platform builders have and trying to optimize platforms have. And all of this is an issue for single region data centers. If you think of having worked with Azure, one of the biggest issues that data centers engineers had there was idle servers. Right now, I think that we're up closing in on 1.7 to 2% of the entire world's energy being used on data centers. And upwards of 60% of that is spent on idle servers. And so trying to optimize this graph and trying to minimize the amount of time our compute is over provisioned is not an imaginary problem by any stretch of the imagination. And so again, having seen the insides of a gigantic cloud provider, this is a problem that they're really trying to figure out how to solve. And again, it's a big issue on a single region. If you're trying to schedule and execute workloads across the world and try to load balance and try to execute as close as possible to an end user request, then this problem, trying to start micro VMs around the world, becomes significantly harder. So I think the simplest question is, do we really need to use micro VMs and containers for a function as a service platform? And from a developer perspective, trying to build functionality and run it serverless, if you need a full Linux operating system in your function, if you need to access like kernel features, or if you need to access like very specific Linux APIs or POSIX APIs, I think the answer is always going to be yes. That's the drawback that you will have for needing something like that. So if you really need to execute Linux specific functionality in your function, then yes. But there's a growing number of use cases where the answer may be no, where they are generic enough, and platforms like Cloudflare Workers show us that with the right API surface, developers can achieve a lot without a full Linux operating system available in their function. And not just Cloudflare Workers, there is a growing number of JavaScript-based serverless offerings around V8 and Dino and other JavaScript runtimes where developers do not have, not even close to having a full Linux operating system API surface, but they are able to achieve significant, uh, achieve a lot and run significant workloads there. So what if instead of using micro VMs or containers, or assuming there's a full Linux environment available for our function, what if we had another unit of execution and deployment for functions? And this is where I want to make the thesis that using WebAssembly as this unit of execution for deployment, unit of execution and deployment for serverless may be able to alleviate a lot of the concerns that at least I presented in the beginning, in particular around cold starts and portability and isolation. So very, very quickly, you can think of WebAssembly as a compilation target for languages such as C or C++ or Rust or Kotlin, and a way to compile traditional Python or JavaScript runtimes into this intermediate format that is compact and portable. The original goal of WebAssembly had been to compile programs like Adobe Photoshop or Google Earth to run into the browser, and it evolved to run in a lot of other places. But importantly, coming from its history of being designed for the browser, WebAssembly had a very, very big goal for isolation. In particular, oversimplifying, if you have your bank application in tab number 1 and a random URL you opened from a message board in tab number 2, you want to absolutely make sure that your random URL cannot access information from your bank account. And so isolation for WebAssembly is a core property. Really, again, isolation is one of the core properties, and more specifically, WebAssembly code does not have access to data outside of its own linear memory, and it does not have access to APIs unless allowed by the host. And originally in the browser, that meant not even DOM APIs were accessible from inside WebAssembly modules. If you expand that to running WebAssembly outside the browser, a WebAssembly component does not have access to any POSIX or Linux APIs unless specifically given access to. And you can be very, very granular in how you give access to specific APIs. Again, stemming from its history in the browser, cross-platform and cross-architecture portability was very, very important for WebAssembly. Once you generate the WebAssembly component or module, you can execute it across operating systems and across CPU architectures. And again, the example in the browser was go to example.com. If it needs to compile WebAssembly components, there's no scenario in which you have to click here to access the Windows website or click here to access the ARM64 website. And so cross-platform, cross-architecture. The other one is, once you access a website, you want it to be instantly available and instantly accessible. So fast startup is extremely important for WebAssembly, same as near native execution. As we'll see in a bit in a short demo, WebAssembly components can start in significantly less than 1 millisecond if already on disk, and can be as little as a few megabytes or even a few kilobytes, depending on what you include in your from your programming language standard library. And then I mentioned already, WebAssembly today supports a wide range of programming languages, and that list is ever growing. And one of the languages with the better support for WebAssembly is Rust. We'll see a short example of building a function in Rust. Um, Python and the Python community is working heavily on CPython compiled to WebAssembly. There's a ton of projects around componentizing Python, the Python runtime, and running it as a WebAssembly component. There's extensive work happening in the Go ecosystem. TinyGo is already a compiler of Go that compiles to WebAssembly and WASI. The main Go project is also working on adding main support for WebAssembly as well. And then there is as usual with JavaScript, a numerous range of WebAssembly support for JavaScript runtimes. We contribute and maintain an implementation of Mozilla's SpiderMonkey compiled to WebAssembly, and so that's how we were able to execute JavaScript serverless functions inside WebAssembly. If you search the Cornell University archive, you'll find a growing number of research papers around WebAssembly in general, and also around serverless WebAssembly in particular. There's also a couple of research groups around universities in San Diego, in particular, around correctness and security. And at Ghent University, where I happen to live, there's a research group focusing on WebAssembly and Kubernetes and IoT and constrained devices as well. So this is not a new topic at all. WebAssembly and serverless and WebAssembly and function as a service is also not a new topic as well. And I mentioned in the beginning, we started Fermyon with the goal of working on WebAssembly tooling, and one of the core principles that I had working on open source has been something must be open source, and a tool around a developer tool in particular must be open source. And so Spin is the first open source project that we released at Fermyon. It is an open source tool for building and running WebAssembly microservices and WebAssembly functions. It uses WebAssembly because it's sandboxed and portable and really, really fast. And as I mentioned, Spin is entirely open source, and it's built on the WoSC10 runtime, WoSC10 being a Bytecode Alliance project. Bytecode Alliance is very quickly an organization that focuses around implementing standards. WebAssembly is a W3 standard, so it's a combined effort between Apple and Mozilla and Microsoft and Google and a bunch of other companies all collaborating on defining the standard. And Bytecode Alliance is one organization implementing tooling for this standard. Mentioned in the beginning, WebAssembly stemmed originally from the browser. Over the last 6 years or so, 5 years, there have been extensive efforts to take WebAssembly and run it elsewhere, and Spin is one of those efforts. Spin is built on top of the WebAssembly system interface, which is a specification that defines how a WebAssembly component can access things outside of its sandbox, and it focuses on out of the browser scenarios. So on WebAssembly on the server fits perfectly well within the purview of what WASI is trying to define. And so you can think of WASI originally as a subset of POSIX. So if you think about how can a WebAssembly component access environment variables, or for the file system, or standard input, standard output, or network sockets, WASI is the standard that defines that, and Spin as a tool is built on top of WASI and built on top of the WoSC10 runtime. The goal of Spin really is to address that ease of use. Cherry picking again from the poll earlier, ease of use and developer experience is something that we care very deeply, and having worked both on platforms and on tools that a lot of developers complained about when it comes to developer experience, we wanted Spin to be a tool that really, really allowed developers to get started as easy as possible. And so the goal of Spin is to make that very, very simple. So there's an extensive library of templates available for programming languages and use cases, and and we're gonna see that in a minute. Spin is entirely open source. It's permissively open source. It's Apache 2 licensed. It is also submitted to the Cloud Native Computing Foundation, which is the Linux foundation, sub foundation, and in the same level as Kubernetes and Helm and a bunch of other cloud native tools. So hopefully in a short while, Spin will be formally a CNCF project. But the main important thing is Spin is entirely open source, permissively licensed, and will always be so. So let's just have a quick look at how to create a WebAssembly application with Spin and run it and ideally deploy it as well. So I mentioned the goal of Spin is to ease that developer concern of how do I take two concerns that are somewhat new, both serverless and WebAssembly, and put them together. So I'm going to choose a template for HTTP Rust. Rust happens to be my favorite programming language. I'm going to call the application HK. And this created a directory for me. And there are two important things to keep in mind when it comes to Spin. The first one is it creates a regular project for a programming language. In this case, it's a simple Rust program, a Rust library. And so it has a cargo toml file. And the second thing is it has a tiny manifest file that contains some metadata and then some settings for my component. I mentioned in the beginning that WebAssembly execution happens inside a tight capability-based sandbox. And so this is the point where you can set things like allowed outbound hosts. For example, this component called HK is not allowed to execute, is not allowed to connect to any outbound HTTP host. Similarly, you can control things like environment variables and access to the file system as well. The goal of Spin is to ease the building of serverless functions, and so this is this is a complete function built in with Spin in the Rust programming language. This happens to be an HTTP function, and so the function takes an HTTP request and it returns an HTTP response. But you can based on the templates here, there are other templates available, not just for HTTP, that you can use for things like MQTT or AMQP or SQS for message-based or IoT scenarios as well. So going to build this function. Behind the scenes, it calls the regular compiler toolchain for this programming language. I'm gonna go back into the spin.toml and share that this is running cargo build. If this was a JavaScript function, this would have run npm build. For .NET and C#, this would have been .NET build. So this is not Spin knowing how to build WebAssembly, but it's calling out to the language toolchain. And this generated a WebAssembly component for us. If we look in the target directory, release hk.wasm, this is a 304 kilobyte WebAssembly component. Depending on what features of the standard library you use or don't use or no standard library, this can go as little as a few kilobytes, like tens of kilobytes, or depending on what libraries and third-party dependencies you include, this could become larger as well. For a standard JavaScript application, this is around 8 megabytes. For a Python project that includes the entire standard library, that's going to be about 20 megabytes. And so it will really depend on the programming language and on the third-party dependencies. But the important thing is you're only compiling the features of the library, the standard library of the language you're using, and nothing else. And at this point, this entire directory, the spin.toml file, which is 390 bytes, and that 304 kilobyte binary is a self-contained full serverless application. I can now run that locally using spin up, which will start an HTTP listener locally on port 3000 and basically make the application available locally. And so that's the local developer experience with spin new, spin build, and spin up. And quickly, I want to have a look at what is actually happening every time I send a request. So the component, the single component in this example has a source field. And that source field points to the WebAssembly file, the WebAssembly component binary that I showed earlier. And so every time there's a request coming to this application, Spin loads the WebAssembly component, creates a new WebAssembly instance, executes the entry point function, the HTTP function, and then executes the completion and then exits. Every single request will create a new sandboxed WebAssembly component that will run in its own isolation sandbox with its own linear memory without access to any other or access to anything else on the system. So, for example, if I have 10,000 requests at once, there will be 10,000 instances that all execute in parallel and then all shut down. If there are no requests happening, such is the case right now, the listener is started locally, but there's absolutely no request incoming. And so depending on how you run this in production, you can have literally zero energy use for it or very little, depending again on how those are spread. There's always an HTTP listener that has to be available, but that can be used for multiplexed for a lot of applications. And so if we're thinking about this at scale, you can get to a scenario where there is zero CPU consumption, zero memory consumption for thousands of applications scheduled on a single node with no traffic, and only consume resources for applications that are in the process of being executed with live requests. Once I finished building this application, I can do something like spin registry push, for example, which will take all of the metadata and WebAssembly components and any other static files that I might need, package it in an OCI artifact. Think this is the same specification that underpins container registries, so you can literally use existing container registry infrastructure and publish this there. You can cryptographically sign it and do same software supply chain policies that you have for containers, and then deploy this in lots of places. One thing that I want to point out is on the machine that I just did the demo earlier, it has it's a regular consumer 20-core CPU. You can run upwards of 1.3, 1.4 million requests in 10 seconds. And again, every one of those requests will create a fresh isolation sandbox for every single request. So the goal of this is not to this is not a realistic scenario because the application is literally just hello world, but WoSC10 and Spin, WoSC10 in particular, is incredibly fast at being able to create and execute sandboxed, untrusted code. Once you get started with Spin, there are features that are built into Spin itself. So, for example, state and persistence were among the things that were in the poll. Spin has a built-in key value store built on top of SQLite, and it also has a relational database based on SQLite as well that just comes built in by default. So if you need something like cache that is not necessarily persistent, you can just use Spin with what comes out of the box. It's also configurable to use Redis or DynamoDB or Azure Cosmos or any other cloud provided store as well. It has support for variables and secrets and lots of other cloud native concerns that you may have come across, and in integrations with things like HashiCorp Vault or SigStore or others. So I'm happy to talk about at the end if anyone has questions about the things that Spin supports or doesn't support. I mentioned once you built the application, you can run it with Spin up. You can just download the Spin binary on our server and just run it as a systemd daemon. You can deploy to Fermyon Cloud, which is the service that we manage and run as serverless. You can deploy it to your own Kubernetes clusters using the SpinQ project, which is another project that we released at Fermyon. We've been collaborating with folks at HashiCorp and Red Hat on Nomad and OpenShift for a couple of years now, so we can deploy Spin applications on those platforms, or you can run it directly in Docker Desktop using Docker Run with a specific containerd class. Again, if anyone's interested in the mechanics and the internal details of any of these, I'm more than happy to talk about it at the end. One of the things I wanna highlight is Spin is built on top of WASM-Time, as I mentioned, the WebAssembly runtime, and on top of the WebAssembly component model. And why that is important and what that is in particular is it's a WebAssembly component that's the core unit of execution and encapsulation here. If you're familiar with the internals of WebAssembly modules and the WebAssembly core specification, it does not specify anything beyond integers and floating points. So the WebAssembly component model comes in on top of it and defines how you can exchange non-trivial data types such as strings or lists or structures. Why that is important is it lets you, on the one hand, statically analyze a component and its capabilities and allow or decline them at runtime. And it also means you don't have to exchange actual memory, unstructured linear memory between host and WebAssembly components. And you can have the interoperability between components and host and components be at a WebAssembly interface level. And to make this even more specific, this is what the Spin platform definition looks like. This is a language called the WebAssembly interface type format, or WIT. And in the Spin project defines the world available for a WebAssembly component. And so this is what the Spin platform advertises, or any Spin platform advertises. I want to draw your attention to line number 6, which is WASI HTTP, which is the standard for how an HTTP handler, an HTTP serverless function is defined. This is a standard that's implemented across WebAssembly runtimes and across services running this. And for example, services running these, you can think of as Fastly's Compute@Edge, or Spin and Fermyon Cloud, or the SpinCube project, or Azure's upcoming CDN compute efforts around Azure Front Door as well. So any place that wants to run a standard WebAssembly HTTP function can implement this WASI HTTP specification, and Spin is one of the tools, both implementing it and building the future of the standard as well. And then if I generate the textual representation of that WebAssembly binary that I built earlier, there's a direct mapping between the binary format and the text format in a tool called WASM Tools. You can see what I meant by each component is statically analyzable. Each component, you can introspect the use of WebAssembly imports. And in particular, I can tell that on line 10, this component needs access to sockets. And so I can decide to decline this, to execute this component in a sort of constrained environment, for example. Or line 11 says this WebAssembly component needs access to a random number generator. Unclear why, so I can choose to decline to execute this component. Or line number 9 says this component must access the file system. I can limit the directory or pre-opened files that this component can execute. And then on line 16, this is the analogous to line 6 here. The platform knows how to execute components that implement WASI HTTP. This component just implements and exports that WASI HTTP incoming handler function. I mentioned Fermyon Cloud, and I mentioned how can I run this across regions? Well, we're in the process of building global support for Fermyon Cloud. What that means is, as a developer, after I do spin use, spin build, spin up, the last step there is, can I deploy this around the world? And can I take that metadata and WebAssembly components and make them available in hundreds of regions, for example? And I'm happy to talk at the end about lots of efforts to optimize ahead of time compile, statically analyze components before deploying it and making them available across the world. Essentially, taking a step back, what we do with Spin and WoSC10 is take untrusted user code and execute it in a multi-tenant environment. And at the core of that, you have to trust the execution engine for it. And in this case, there is extensive work and research that went into security and correctness for the WoSC10 project. There is 24/7 continuous fuzz testing for the project. And so we have a pretty high degree of trust in the runtime itself. And there are mitigations for Spectre and other and other security work ongoing. So if you're interested in this, there's a phenomenal article by Nick Fitzgerald around security and correctness in WoSC10 and a few people at Fermyon that work on the security stance of WoSC10. What if you don't trust just a WebAssembly runtime? What if you need beyond a simple WebAssembly runtime? Well, there's a project that some of us started before leaving Microsoft called Hyperlight, which essentially takes a light hypervisor and essentially runs WebAssembly inside it. There's a version of the Spin project that integrates with KVM and the Rust VMM project that allows you to instantiate a micro VM for every single request. The main difference being the kernel in there is incredibly minimal. There's nothing beyond the ability to execute the same WebAssembly component. And so you can still get hundreds of thousands of requests per second. You're not going to run a full Linux operating system, but you have a guaranteed isolation sandbox between untrusted user code and the rest of the system. But for the most part, security and correctness in WoSC10 is high enough, and the work ongoing there is incredibly robust that there's significant use of WoSC10 without anything else on top of the isolation that WoSC10 itself provides to make it trustworthy. For the last couple of years, we've been executing WebAssembly functions at scale with Fermyon Cloud. There are a few thousand developers deploying WebAssembly functions and executing millions of requests there. And so there are a couple of things that we need to do proactively to be able to execute those. We can control the amount of memory, CPU time, network bandwidth, and more than that. But those are the core ones that we can control and terminate at any given point in time. You can set very strict limits to memory and CPU time. You can allow them. We can centrally compile WebAssembly ahead of time. I mentioned in the beginning that WebAssembly is an intermediate portable format, which means that to execute on a specific CPU architecture, you have to transform from WebAssembly to almost machine code that is specific to that CPU architecture. And so you can either just-in-time compile or ahead-of-time compile. If you know the environment and if you know the data center that you're going to deploy and execute WebAssembly into, you can centrally ahead of time compile this WebAssembly to the specific OS and architecture and distribute highly optimized machine code, which is something that we do as well. We optimistically schedule thousands of functions on any given node for Fermyon Cloud today. We do this because of two main reasons. The first one is the use cases that we've seen developers use in Fermyon Cloud favor short and bursty executions compared to long-running functions. That's the first one. And the second reason why we can schedule thousands of them is because we incur zero resources beyond disk usage for idle applications. And so a single 8-core VM that we use in Fermyon Cloud today has probably around 3,000 to 3,500 WebAssembly components scheduled on top of it. And those are only instantiated when there's an incoming request. We have a mix of Linux 886 and ARM64 nodes, and depending on efficiency, region availability, other kind of constraints like cost, for example, we can decide very, very late what platform architecture to use. And this has zero impact on developers building and deploying those applications. Another important thing is we can suspend in memory any given function that is waiting on I/O. So if you have a function that is making a database query that takes 6 seconds, for example, we suspend that in memory and execute other things, and it consumes no CPU at all when that happens. And we do that for any asynchronous function boundary, which is one of the reasons why we put a lot of work into the WebAssembly component model and the async implementation of it. But that is something that I've not seen being used at a function level before, and at a this kind of workload level before, which allows us to have pretty relaxed total wall time limits for our functions, in particular with things like AI inferencing operations that can take like 30 seconds. If you're waiting for I/O from your caller, you can execute anything else in the meantime as well. And then for high core count machines, like some of the ARM64 machines that we're using, some of them can have like 384 cores, for example. We have to pin the WASM runtime to a subset of cores and potentially have multiple instances of it, because IPI is interprocess interrupts is something that we've seen has a significant impact, which we don't really see on low core count machines. If anyone's interested in in Discord or in the Q&A section about standardization for HTTP functions or beyond, observability, debugging, inferencing, or Spin is a project that today runs in cars and satellites and a lot of other places, I'm happy to talk about. Please have a look at the Spin project. Is again entirely open source and will always be so. And thank you for having me. I'm happy to answer any questions.
Okay, so if you mind, you can ask questions and I will repeat them here so that they are recorded in the Zoom meeting, okay? Because we cannot hear you from this machine. Or I can, yeah. We have the other one, but I feel it doesn't work. Hello, yes. Also, you can move if you want. It's just for your convenience.
Well, the first question is coming up. I'm looking at Discord. There's something that I do want to I missed pointing out in the presentation. Obviously, there's a drawback to using WebAssembly, which is you'll not be able to assume that there's a Linux operating system available for your component to use. And so, for example, Python packages that assume like a shared library that assumes a Linux environment and a Linux operating system and Linux dependencies, that will most likely not work right now in WebAssembly. And so that's the drawback to having access to this instantly really fast startup.
I'm not sure if everybody can hear it, but I have a quick question.
Yes, yes, we can.
Okay, very good. Thank you. So I have a little bit experience with WebAssembly, and one thing I run into is use of Rust, or in particular, Rust toolchain. So
Yep.
do you think that Rustification will continue, or it will be easy to use it from other programming languages? Because I think right now, if you want to do HTTP, that would be mostly Rust, if I understand correctly. The current WASI, support 0.2.
That's a great question. Today, I can point you to .NET 9 has support for WASI HTTP, for example, so you can use the actual .NET standard library system.net to make HTTP requests. So while that is still work in progress in a lot of language tool chains, C#, Rust, TinyGo, and JavaScript all have robust support at this point for this. And to your point about the Rustification of WebAssembly, that is a pretty amusing coincidence that a lot of the early people in the WebAssembly ecosystem just happened to work on Rust compilers and the Rust toolchain, which is why Rust is so has so good support for WebAssembly. And so there's nothing inherent in Rust other than it has about 1.5 to 2 years head start because of the people using WebAssembly were just Rust people.
Okay, so we have a question here, Phil. He will ask it himself.
Right, thank you. Using containers, which are cross-compiled or multi-architecture container images, from my experience, we often had problems where people have to, or basically the same application compiled to X or to AMD64 and to ARM64 have very different, or can have very different CPU and memory requirements at runtime, or behave differently in terms of resource consumption. How does WebAssembly deal with that? Like, does it help if you deploy, for example, your serverless applications to like heterogeneous nodes?
Yeah. The big advantage of using WebAssembly for this is you can a developer will compile to WebAssembly, and then as the platform builder or runner or optimizer, you can decide later if it runs better on x86 or ARM64. For example, that is a real scenario right now where there are a couple of optimizations in the CraneLift compiler, which is the compiler that WASM uses behind the scenes, where it has a lot of optimizations for Intel processors that are missing for ARM64, for example. And so there are some workloads that will just run better on x86, on an Intel in particular. And you can decide very late to either move a workload from ARM64 to Intel or just run it directly there after a developer has built and deployed that application. So that is still the case, but there are some mitigations around it. And the more people use these architectures, the better optimizations that are being built as well.
Very good. We have another question there.
Hi. So you mentioned Hyperlight, which is for, again, isolating WebAssembly. What is the motivation behind that? Why would you want to use that if WebAssembly has security as a core concept?
There are a couple of scenarios where I think that there are different use cases that we're talking about. I think the majority of use cases that we see are around things like media use cases and manipulating HTTP headers and very lightweight processing. Whereas there are how do you call those? There are just entire industries that will just not allow non-hypervisor workloads to run on the same machine or even on different machines. And so it's not there's no scenario that we've observed where the WASM security sandbox is not enough, but we have seen, for example, someone like Azure where they have the Pepsi and Coke problem, where they just don't want to run untrusted code for very specific workloads. So I think for at least how I think about Hyperlight and the KVM project that we're doing are, if something incredibly bad happens, there's the ability to isolate the specific workloads, as opposed to by default, every single function will run with its own kernel. And so that's how I think about it until we find a very, very critical scenario where we need to, we won't use a hypervisor micro VM for every function.
Okay, so it's not technically motivated, but more organizational.
Yes.
Oh, okay, thank you.
And if you think about platforms built on top of V8, for example, anything like Cloudflare Workers or others, those use a V8 isolate, which has, depending on how you look at it, very similar or lower security boundaries than WebAssembly instances as well. And they run billions of requests around the world.
Hey, Radu, thanks for the great talk. I'm Anirudh from Georgia Tech. And I know you spoke about the security isolation and also the fact that you can control the CPU resources for the function. I was wondering if you've noticed or observed use cases that demand performance isolation, like where the application developer kind of specifies this is the amount of concurrency I can tolerate and something along those lines, Have you noticed that?
Yes, because of the clustering of use cases that we see, most of the applications are not CPU bound, but are network bound in most cases. And so because we're able to suspend all of those in memory, we can have a high degree of concurrency for those use cases. For scenarios where applications are CPU bound, we have experimented with defining that in the spin manifest and essentially being able to say, I need to run this workload, I need to run this component in an environment where I can have N concurrency. That's not something that's built into Spin right now. Again, mainly because use cases we've seen are network bound and not CPU bound. But that doesn't mean that there aren't scenarios where that might be the case. I'd love to chat about some of those scenarios if you have them.
Thank you.
Thank you very much, Radu, for the talk. It was very, very nice, very interesting too.
Thanks.
I don't know if you have something more to say. We are very delighted to have you here today.
Awesome. Thank you so much. I'm on Discord and I'm online probably more than I should be. So if anyone wants to chat about anything WebAssembly or serverless, I'm more than happy to.
Sure.
Thank you so much.
As I said before, just post the questions on Discord. They are persisted there and we can take a look at them. Thank you very much, Radu, again.
Awesome. Have a great rest of your conference.
Thank you.